Welcome to Module 2A of the Avalanche Level 2 series. In this module, we will focus on weather. Since there's a lot of material to cover, we have broken this subject into 3 parts. Part 1 will focus on general weather topics. An understanding of general weather principles is necessary to understand the effect weather has on the snowpack and avalanche risk. Part 2 will focus on mountain weather. When we say mountain weather, we mean the interaction between large-scale weather patterns in the mountains and how mountains modify weather. Part 3 will focus on how weather affects avalanche risks and what tools we use to track and assess the weather and its impact on risk. So let's dive into it. We're going to start with some basic topics that you may have been exposed to in your high school or college science courses. The first concept is energy. Energy is a characteristic of matter that represents the ability to do work or produce heat. Energy cannot be created or destroyed, only converted from one form to another or transferred from one object to another. Some common forms of energy are chemical energy, as in the energy in bonds between atoms, kinetic energy, present in any object in motion, potential energy, for example, the energy in a cornice, radiative energy, such as the solar energy from the sun, and thermal energy or heat. Temperature is a measure of thermal energy. Heat absorbed by an object raises the temperature of that object. Conversely, heat released from an object lowers the temperature of that object. The calorie is the unit of heat energy. 1 calorie is defined to be the amount of thermal energy needed to change the temperature of 1 kilogram of water by 1 degree C. So why do we care about energy? Well, energy, particularly solar energy, is the driving force behind weather, as we'll see in this module. All of the macro weather phenomena is determined by uneven solar heating in the atmosphere. Moreover, the snowpack is also strongly influenced by solar energy. Throughout this module, in the snowpack module, we will discuss a concept called energy or radiation balance. Radiation balance is the net sum of the radiation absorbed and emitted by an object. This slide shows an example of the components of radiation balance. Solar radiation is emitted from the sun. Some will be absorbed or reflected back by the clouds, and some will be reflected back from the Earth's surface, and some will be absorbed by the Earth's surface. The solar radiation that is absorbed by the Earth's surface will increase the temperature of the surface. If this were snow, for example, the top layers of snow would absorb this thermal energy and heat up, changing the crystal structure of the surface layers. In parallel with the solar radiation being absorbed and reflected, long-wave radiation is emitted from the surface. All objects emit long-wave radiation. This radiation will be emitted into the atmosphere. Some will be absorbed or reflected by clouds, and some will be transmitted into space. The net sum of these two sources is radiation balance. One or the other will dominate at different times of the day or in different seasons as the angle of incidence of the solar energy on the Earth changes. So energy is one characteristic of matter. 2 other key characteristics are mass and volume. In fact, these characteristics are related. As energy is added or removed from an object, its mass and volume will change, as shown on this slide. All matter is made up of atoms. These atoms have a kinetic energy that is a function of the temperature of the material. As energy is added to or removed from an object, the kinetic energy of the atoms that make up the material increases, and the object can change its phase. The 3 phases of matter are solid, liquid, and gas. Each phase has a characteristic energy level which determines the volume and mass of a sample of matter. This slide shows the effect of increasing the temperature of a material. As you can see, as the temperature increases, the material transitions from a solid to a liquid and then from a liquid to a gas. These transitions occur as thermal energy causes an increase in kinetic energy of the molecules that make up the material. The Earth is surrounded by a layer of gas that is referred to as the atmosphere. The atmosphere is primarily composed of nitrogen and oxygen in the percentages shown on the slide. The 1% of other gases include water vapor in its various phases. Although a relatively small percentage of the gases in the atmosphere, it's the water vapor that accounts for all the precipitation we experience. The solar energy from the sun heats the atmosphere and creates the weather, and the mountains influence these weather patterns, as we will show shortly. When we talk about atmospheric pressure, we're referring to the weight of a 1-inch column of air from the surface of the Earth to the edge of the atmosphere. This is measured in millimeters of mercury, or millibars. Atmospheric pressure is sometimes referred to as barometric pressure. As you might expect, the atmospheric pressure varies as you go up in altitude, since the amount of air above you is reduced. And the atmospheric pressure varies as you travel around the globe due to uneven heating from the sun. The reference for atmospheric pressure is typically set at sea level as 760 millimeters of mercury, or 1,013 millibars. This pressure is referred to as 1 atmosphere. The images on this slide show how atmospheric pressure varies with altitude. The image on the left shows atmospheric pressure versus altitude as an inverse function. Altitude increases, atmospheric pressure decreases. The image on the right relates a common landmark, Mount Everest. As you can see, at the highest point on Earth, the atmospheric pressure is only about 30% of sea level pressure. Vapor pressure is the pressure exerted by a gas on the surface of a liquid. In equilibrium, the number of gas molecules going from a liquid to a gas is equal to the number of molecules going from the gas to the liquid. When atmospheric pressure is greater than the equilibrium vapor pressure, no water molecules go from the liquid to the gas. There's no evaporation. The temperature at which the vapor pressure is equal to the atmospheric pressure is known as the boiling point. So why do we care about this? Well, in the snowpack, there will be a vapor pressure gradient from the surface of the snow to the interior of the snowpack. This vapor pressure gradient is the primary factor that determines what kind of snow crystals we will get in the snowpack and whether the snow crystals will be well bonded or poorly bonded. As we already mentioned, atmospheric pressure varies with elevation as air density decreases. Temperature variations will also reduce air density. Temperature variations can occur due to changes in latitude, distance from the equator, which reduces the angle of incidence of the sun's solar energy. Temperature variations occur due to the rotation of the Earth. These are referred to as diurnal variations. And temperature variations can occur due to the Earth's rotation around the sun. These are referred to as seasonal variations. All of these temperature variations result in air density changes, making air masses more or less buoyant than adjacent masses. This temperature variation across the surface of the Earth results in uneven heating, which leads to variations in air density and creates convective currents that we refer to as weather. This slide shows the seasonal variation due to the Earth's rotation around the sun. This results in the seasonal temperature variation discussed above. The various sources of temperature variation we discussed create the weather we experience. Differences in air temperature and density result in low and high pressure zones around the planet. This drives convective airflow, the equatorial polar movement, and the jet stream. More localized airflow between high and low pressure zones, coupled with the Earth's rotation, result in the Coriolis effect in cyclonic and anticyclonic airflow and local prevailing winds. In the northern hemisphere, air flows in a clockwise direction around high-pressure systems. This is called convergent or cyclonic flow. Air flows in a counterclockwise direction around low-pressure systems. This is called divergent or anticyclonic flow. Air will flow from high-pressure system to low-pressure systems. The greater the pressure difference between the two systems, the greater will be the velocity of wind flowing from one to the other. Let's look at some of these airflows in more detail. This graphic shows the equatorial polar airflow due to the temperature variations from the equator to the poles. Air at the equator is warmed and rises and forms a low pressure region. This air flows north and south, increasing the air density in that region, subtropical highs. As the warm air rises, it is cooled and sinks back to the Earth's surface and flows back towards the low pressure zone at the equator, and the process repeats. This process repeats in the subpolar regions and the polar regions. All these circular airflows are linked, and when coupled with the Earth's rotation, result in the jet stream. The air at the higher altitude, 25,000 feet and up, is funneled from cell to cell and creates the jet stream shown in the graphic. The jet stream is also affected by El Niño and La Niña forces. El Niño and La Niña create a quasi-periodic climate effect that occurs roughly every 5 years. Known as the El Niño Southern Oscillation, or ENSO, this is a variation in ocean surface temperature that affects the air surface temperature. This creates large blocking high pressure or low pressure cells that shift the jet stream in a northerly direction for La Niña or in a southerly direction for El Niño. The Coriolis effect occurs due to the rotation of the Earth. In a static system, air would flow down a pressure gradient from high pressure to low pressure in a straight line. However, due to the rotation of the Earth, a Coriolis force is created that bends the airflow in the direction of the force. In the northern hemisphere, this bends the airflow in a counterclockwise direction. In the southern hemisphere, this bends the airflow in a clockwise direction. This explains the circular patterns we see during a tropical storm or hurricane. The pictures on the bottom right show a hurricane in the northern hemisphere on the left and the southern hemisphere on the right. The uneven heating of the atmosphere results in pressure systems and air movement, as we've been discussing. These bodies of air are subject to lifting mechanisms that cause vertical movement. The four lifting mechanisms of interest are convection, cyclonic and anticyclonic, frontal, and orographic lifting. For our purposes, we will discuss when we discuss mountain weather in part 2, orographic lifting will be the most important mechanism. Why is this vertical movement of air of interest to us? Well, as the air rises, it expands and cools. As the air expands and cools, the moisture capacity of the air increases. This means that the air can hold less water, and any excess water vapor condenses and forms water droplets, clouds, and rain or snow depending on the temperature. This slide shows the mechanism of convective lifting. The sun heats the ground heats the air in contact with the ground. As the air temperature increases and the warm air rises and is replaced by cooler, more dense air, this cycle is repeated, creating air currents that rise and fall due to solar heating. We've touched on cyclonic and anticyclonic air movement in a previous slide. In this case, the circular movement of the air also results in vertical movement. In clockwise movements around a high pressure system, air will diverge, flow away from the high pressure to the lower pressure areas. This will draw air down from the high into the high to replace the air that diverges away from the high pressure areas. Similarly, the counterclockwise movement of air around a low pressure system will result in air rising away from the system as air comes in from an adjacent high pressure system. One form of lifting we all may be familiar with is frontal lifting. This is what the weather person on the news talks about when they discuss fronts moving through the area. Frontal lifting occurs when two masses of air collide. If the masses of air are at different temperature and pressures, they will not mix. An advancing body of warm, moist air, as shown in the top figure, will ride over a receding cold air mass. This is known as a warm front and will typically bring rain along the front where the warm and cold air masses meet. An advancing body of cold air, known as a cold front, will lift the receding warm front as shown in the lower picture. So this brings us to the end of part 1 of the weather module. In part 2, we will shift our focus from the general weather concepts discussed here to mountain weather.